Modules and homological algebra, lecture 12, problem session. Problem 1. Determine the canonical decomposition into cyclic groups for the finitely generated abelian group A, defined as the cokernel of the homomorphism from Z3 to Z4, given by the following matrix: 2, 2, 2, 2, 4, 4, minus 4, 2, 6, 8, 6, minus 2. Solution. In order to solve this problem, we need to reduce this matrix to its Smith normal form. Clearly, the greatest common divisor of all entries of the matrix is 2. Therefore, we can use the number 2, which stays in position 1, 1, and elementary row operations to eliminate all other non-zero entries in the first column. So we subtract row 1 from row 2, we add twice row 1 to row 3, and we subtract 4 times row 1 from row 4. We get the following matrix: 2, 2, 2, 0, 2, 2, 0, 6, 10, 0, minus 2, minus 10. Here, we can use the element 2 in position 1, 1 and elementary column operations to kill all other elements in the first row. And we get the matrix 2, 0, 0, 0, 2, 2, 0, 6, 10, 0, minus 2, minus 10. Now again, it is clear that this number 2 is the greatest common divisor of all entries of the matrix, which is obtained when we delete the first row and the first column. So we can use the 2, which stays in position 2, 2, and elementary row operations to eliminate all other non-zero entries in the second column. So we subtract 3 times the second row from the third row, and we add row 2 to the fourth row. And we get the matrix 2, 0, 0, 0, 2, 2, 0, 0, 4, 0, 0, minus 8. Now in this matrix, we can use 2 in position 2, 2 to eliminate all other non-zero entries in the second row. So we use the column operations. So we subtract the second column from the third column, and we get the matrix 2, 0, 0, 0, 2, 0, 0, 0, 4, 0, 0, minus 8. So now here, if we delete the first and the second row and the first and the second column, we get this small matrix. And here, of course, 4 is the greatest common divisor. So we use 4 to eliminate minus 8. So we add twice the third row to the fourth row, and we get the matrix 2, 0, 0, 0, 2, 0, 0, 0, 4, 0, 0, 0. So this matrix is the Smith normal form of our original matrix, and so we can use it to read off the answer. Note that all diagonal elements are powers of the prime number, so we just write for the first element we get the direct sum on z divided by 2z, so this is a cyclic group of order 2. Then we have for the second 2, we also have the cyclic group of order 2z divided by 2z. For the third element 4, we have the cyclic group of order 4, which is z divided by 4z. And then, since we have one additional row, there is no diagonal element there, so we get a direct sum on just the free group z. So the free abelian group of rank 1. And the direct sum of these 4 summons is the answer. Problem 2. Determine the real normal form for the following matrix: 1, 1, 1, 0, minus 2, 1, 0, 1, minus 1, 0, 1, 1, 0, 1, 0, 1. As usual, in order to determine some normal form for some matrix, we first need to compute its characteristic polynomial in order to see what kind of eigenvalues we have. So we take our matrix, subtract lambda on the main diagonal, and compute the corresponding determinant. In this determinant, we see that we have the number minus 1 in the third row in the first column. So the most reasonable thing to do here is to swap the first and the third row and to multiply this third row, which will now be first, by -1 to make this number 1. So swapping the rows gives us the minus sign, multiplying by -1 gives us another minus sign, and they cancel each other. So now we have the determinant of the matrix 1, 0, lambda -1, -1, -2, 1 minus lambda 0, 1, 1 minus lambda 1, 1, 0, 0, 1, 0, 1 minus lambda. So now we can use the elementary row operations and this 1 to eliminate all other elements in the first column. So we add twice the first row to the second row, and we multiply the first row with lambda -1 and add to the third row. So we get the following matrix: 1, 0, lambda -1, -1, 0, 1 minus lambda, 2 times lambda -1, -1, 0, 1, lambda -1 squared plus 1, 1 minus lambda, 0, 1, 0, 1 minus lambda. As a next step, we know that now we can just delete the first row and the first column because of these zeros. And again, we have 1, let's say here with 0, so we swap the fourth and the third row. So our first row will now be the first one. When swapping the rows, we need to add the minus sign to the determinant, so we get the determinant of the matrix 1, 0, 1 minus lambda, 1, lambda -1 squared plus 1, 1 minus lambda, 1 minus lambda, 2 times lambda -1, -1. Now in this determinant, what we can do, we can use 1 here to eliminate all other elements in the first column. So we subtract row 1 from row 2, and we multiply row 1 with lambda -1 and add to row 3. And we get minus the determinant of the following matrix: 1, 0, 1 minus lambda, 0, lambda -1 squared plus 1, 0, 0, 2 times lambda -1, minus lambda -1 squared plus 1. Because of these zeros, this determinant is equal to the determinant of the 2 times 2 matrix, which is obtained when we delete the first row and the first column. And then because of this 0, the determinant is just the product of these two diagonal elements. Note that we have the minus sign here and the minus sign here. And so the characteristic polynomial is the square of lambda -1 squared plus 1. So this polynomial has complex roots, 1 plus minus I, both of multiplicity 2. There are no real roots at all. So in our real normal form of the matrix, we will only have real cells. There will be no Jordan cells at all, because we only have complex roots. So let us determine the geometric multiplicity of one of these complex roots. Let's take 1 plus I. Since the second root is the conjugate of 1 plus I, the geometric multiplicity of the second root is equal to the geometric multiplicity of the first root. So in order to determine the geometric multiplicity of a root, we need to solve the homogeneous system of linear equations whose matrix is obtained from the original matrix by subtracting our eigenvalue, the root 1 plus I, on the main diagonal. We do that, and we have the matrix minus I, 1, 1, 0, minus 2 minus I, 0, 1, minus 1, 0, minus I, 1, 0, 1, 0, minus I. So here what we can do, we multiply the third row with -1 and swap it with the first row. So we get the matrix 1, 0, I, minus 1, minus 2, I, 0, 1, minus I, 1, 1, 0, 0, 1, 0, minus I. Now we can use this 1 to eliminate everything else in the first column. So we add twice the first row to the second row, and we multiply the first row with I and add to the third row. And in this way, we get the matrix 1, 0, I, minus 1, 0, minus I, 2I, minus 1, 0, 1, 0, minus I, 0, 1, 0, minus I. So the third and the fourth row are the same. We can delete one of them. And we have 1 here in the second column, so we swap rows 2 and 3 to get this 1 in position to 2. Now we have the matrix 1, 0, I minus 1, 0, 1, 0 minus I, 0 minus I, 2I minus 1. So now we use this one to kill this minus I, so we multiply the second row with I and add to row 3. And we get the matrix 1, 0, I minus 1, 0, 1, 0 minus I, 0, 0, 2I, 0. Now we divide the third row by 2I to make the number at the position 3, 3 to equal to 1. And now we use this 1 to kill this I in position 1, 3. So we simply subtract I times the third row from the first row. And we have the final matrix 1, 0, 0 minus 1, 0, 1, 0 minus I, 0, 0, 1, 0. So it has rank 3, so there is one linearly independent solution, which means that the geometric multiplicity of 1 plus I is 1. So we have one linearly independent eigenvector with eigenvalue 1 plus I. And similarly for the complex conjugate, we have exactly the same answer. So this means, since both these eigenvalues have algebraic multiplicity 2 and geometric multiplicity 1, the Jordan normal form of the original matrix over the complex numbers is the direct sum of two blocks. Each block is of size 2 times 2, and the first block is for the eigenvalue 1 plus I, and the second block is for the eigenvalue 1 minus I. And this means that the real normal form consists just of one real cell of size 4 times 4, which corresponds to these two complex conjugate eigenvalues. So we have one real cell of the size 4 times 4, and for 1 plus I, we have 1, 1 minus 1, 1. So this is the 2 times 2 matrix, which has complex eigenvalues 1 plus I and 1 minus I. So we put it on the diagonal here, on the diagonal here, and the identity matrix here. So the answer is the following matrix: 1, 1, 1, 0, minus 1, 1, 0, 1, 0, 0, 1, 1, 0, 0, minus 1, 1. This is the real normal form of the original matrix. Problem 3. Classify indecomposable finite dimensional modules over the following quiver over the complex numbers. So the quiver consists of 3 vertices, 1, 2, and 3, and 2 arrows, the arrow alpha from 1 to 2, and the arrow beta from 3 to 2. Solution. A finite dimensional module over this quiver is the following thing. So we have 3 vector spaces v1, v2, and v3, which correspond to our vertices 1, 2, and 3. We have the linear operator f alpha from v1 to v2, so this represents the action of alpha. And we have the linear operator f beta from v3 to v2, this represents the action of beta. v1, v2, and v3 are finite dimensional complex vector spaces, and f alpha and f beta are linear operators. By choosing some bases in these vector spaces v1, v2, and v3, we can represent f alpha and f beta as matrices. So let us say that the matrix M represents f alpha and the matrix N represents f beta. Since f alpha and f beta are linear operators with the same codomain v2, the matrices M and N, they have the same number of rows, actually rows, so they correspond to the codomain of the linear operator. And if we rechoose bases in v2, we should do the same row operations to M and N simultaneously. So we will write these two matrices next to each other, M, then vertical line, and then N. And in this way, we see that they will have the same rows and then different columns. They have different domains, but the same codomain. The freedom which we have is we can choose different bases in v1, v2, and v3. And what we need to do, we need to find some easy canonical form to which we can reduce any pair of the matrices M and N using the different choice of bases in v1, v2, and v3. If we choose a new basis in V2, this means that we do elementary row operations with the matrices M and N simultaneously. Choosing a different basis in V1 means that we do elementary column operations with M and nothing with N. And choosing a different basis in V3 means that we do elementary column operations with N and nothing with M. Recall that if we have any matrix, then using independent row and column operations with this matrix can be reduced to the following canonical form. So we have the identity matrix in the upper left corner, and the rest is 0. Note that this identity matrix is a square matrix, while the original matrix doesn't have to be a square matrix, and these blocks 0, 0, and 0, they are just rectangular blocks of appropriate sizes. So E is a square matrix, the identity square matrix, and the zeros are rectangular blocks of appropriate sizes. So this claim is actually equivalent to saying that if we take a quiver which consists of 2 vertices and 1 arrow between them, then this quiver has 3 indecomposable modules. Namely, the first module is a simple modular at the vertex 1, so at this vertex it's 1-dimensional, in the other vertex it is 0-dimensional, and the arrow is a 0 map. The second module is a simple module at the vertex 2. At this vertex it's 1-dimensional, at vertex 1 it's 0-dimensional, and the arrow is the 0 linear operator. And then we also have the indecomposable module, which is 1-dimensional at each vertex, and we have the identity operator between them, which represents the arrow of our quiver. We proved that this is the classification of indecomposable modules over the quiver during the lecture. So now we have our pair M and N of matrices with common rows. So we can start with this pair, and applying the previous slide to M, just forgetting N, we can reduce this pair to the following form. So we reduce the matrix M to the canonical form E0, 0, 0, and the matrix N changes in some way which we don't know. So we separate it in the two parts N1 and N2, where N2 is the part which corresponds to our identity, and N2 corresponds to these zeros. So here now we use a double vertical line to separate M's from N's, because the usual lines will separate the parts of each matrix separately. So N1 and N2 are unknown matrices. So we start from M line N, we do something with M, and something will be done with N as well, and it will be transformed into this pair of matrices N1 and N2. Now we can apply the previous slide to the matrix N2 and reduce our problem to the following form. So we have now the matrix M, which looks like E0, 0, 0, 0, 0, and the matrix N2 now looks like E0, 0, 0, while N1 gets split into two unknown matrices N3 and N4. So now in this matrix, we have the identity matrix here, and if we will add the rows in this second row to the rows in the first big row, we can eliminate all elements in the matrix N3, and this will not change anything else because of the zeros. So we can reduce the previous matrix to the following form: E0, 0, and 4, 0, 0, E, 0, 0, 0, 0, 0. And now we can apply our reduction statement to the matrix N4. So we can reduce the matrix N4 to the form E0, 0, 0. Note that now here we have to be careful, because this means that we will change rows of N4. We can apply elementary row operations to N4, and this will affect this matrix E. But this is an invertible matrix, and whatever can be done to it using the elementary row operations can be undone using the elementary column operations, which will not affect anything else. So this means that at the end, the final canonical form of our matrix looks as follows. So we have the matrix E0, 0, 0, E0, 0, E0, 0, 0, 0, 0, 0, 0, E, 0, 0, 0, 0, 0, 0, 0, 0. And there are no parameters left. So in particular, we have a finite number of direct summands. And if we look carefully at this form, we see that this canonical form has actually exactly 6 direct summands, and these are the indecomposable modules of the original quiver, which looks as follows. First, we have the simple module in the vertex 1, so it's one-dimensional at that vertex, zero-dimensional everywhere else, and all operators are 0. We have the simple module at the vertex 2, it's one-dimensional there, zero-dimensional everywhere else, and all the maps are 0. And similarly, we have the simple module at the vertex 3, so it's one-dimensional there, zero-dimensional everywhere else, and all allos are 0. Next, we have the indecomposable module, which is one-dimensional at vertices 1 and 2, and the corresponding arrow between 1 and 2 is given by the identity linear operator. It is zero-dimensional at vertex 3, and the second arrow is a 0 map. Then we have the indecomposable module, which is one-dimensional at vertices 2 and 3, and the corresponding arrow from 3 to 2 is given by the identity linear operator. Then this module is zero-dimensional at vertex 1, and so the arrow from this vertex to 2 is the 0 operator. And finally, we have the module which is one-dimensional at all vertices, and where we have the identity operators for both arrows. And this is the answer to our problem. And finally, problem 4. Let R be the ring of Gaussian integers. Note that this ring is a principal ideal domain. Define the module V over R as the cokernel of the homomorphism from the free module of rank 2 to the free module of rank 3, given by the matrix I minus I 2, 0, 2, 2. Define W as a cokernel of the homomorphism from the free module of rank 3 to the free module of rank 2, given by the matrix 2, 2, 4, 4, 4, 8. Determine whether V and W are isomorphic. Solution. In order to determine whether these two modules are isomorphic, we need to write each of them in the canonical decomposition. So we need to reduce both these matrices to their respective Smith normal forms. Okay, we start by computing the Smith normal form of the first matrix. Let us note that the element I is invertible in Gaussian integers, so we can divide the first row of the matrix M by I to get the matrix 1 minus 1 to 0 to 2. So now we can use this 1 to eliminate everything else in the first column. So we subtract twice the first row from rows 2 and 3, and we get the matrix 1 minus 1, 0, 2, 0, 4. Now we can use the element 1 in position 1, 1 to kill all other elements in the first row using elementary column operations. So we get the matrix 1, 0, 0, 2, 0, 4. Now, if we delete row 1 and column 1, we are left with the matrix 2 and 4. Here, of course, 2 is the greatest common divisor, so we can use it to kill the 4. We just subtract twice row 2 from row 3. And we get the matrix 1, 0, 0, 2, 0, 0, which is the Smith normal form of M. Let us note that the Gaussian integer 2 is not a prime. It is a prime in the ring of integers. It is not a prime in the ring of Gaussian integers. In fact, 2 is equal to 1 plus I times 1 minus I. So each of them is a prime, but they are also associated. So the prime decomposition of 2 is minus I, which is an invertible element, times 1 plus I squared. So 2 is actually associated to a power of a prime in Gaussian integers. So the canonical decomposition of V will look as follows. So we have the free summand Zi, and then we have the torsion summand Zi divided by 1 plus I squared Zi. This is the canonical decomposition of the first module. Now we need to try to compute the Smith canonical form of the matrix N, which is 2, 2, 4, 4, 4, 8. The greatest common divisor is 2, so we can use this 2 in the position 1, 1 to kill everything else in the first column. So we subtract twice the first row from the second row, and we get the matrix 2, 2, 4, 0, 0, 0. Now we use 2 at position 1, 1 to kill everything else in the first row using elementary column operations. So we subtract the first column from the second column and twice the first column from the third column. And we get the matrix 2, 0, 0, 0, 0. This is our Smith's canonical form for n. Now we can read off the decomposition of the module W. So it has one free part, the free module of rank 1, which corresponds to the 0, and then the free module divided by the ideal generated by 2. As we have already seen before, up to an invertible element, 2 is the second power of the prime 1 plus I. And so our decomposition is the free summand zi and then the torsion summand zi modulo 1 plus I squared zi. And now by comparing the decompositions, we see that V is isomorphic to W. I think it is fair to say that this outcome is unexpected from the original forms of the matrices. Now some problems and questions at the end. Question 1. Let A be the abelian group given by the cokernel of some homomorphism from Z4 to Z5. Show that A is infinite. Question 2. Let A be the abelian group given by the cokernel of the homomorphism from Z5 to Z4. The question is, can A be infinite? Question 3. Determine the real normal form for the matrix 1, 0, 1, 0, 1, 0, minus 1, 1, 1. Question 4. Let R be a principal ideal domain and A and B two elements in R. Determine sufficient and necessary conditions for the modules R divided by the ideal generated by A and R divided by the ideal generated by B to be isomorphic. And question 5. Let R be a principal ideal domain and A, B, and C three elements in R. Determine sufficient and necessary conditions for the direct sum of R modulo the ideal generated by A plus R modulo the ideal generated by B to be isomorphic to R divided by the ideal generated by C. Thank you very much and see you next time.